Hello, everybody. I hope you're having a good weekend. So I decided to make this video to help you guys through the calculations for this lab. What you will need to do these calculations are the procedure, part A, B, C, and D. All of this contains all of the volumes and molarities that you will need for your calculations for the tables below. So make sure that you have this information. You are constantly referring back to it and you use the volumes that they give you here for your molarity and dilution calculations. So let's just get to it. Okay, so here we go. Part A. For part A, all we did was take the pH of the solution and nothing more. So for this, it should be relatively straightforward, I believe. So the pH of the solution, I'm going to use an example here that I had from somebody. The concentration is whatever you wrote on the bottle. I believe it was 1.00 or 1.001. For simplicity, I'm going to use 1.00. So 1.00, this is a concentration, so it's molar. The pH of the solution, I believe one example that I saw was 2.45. You should have recorded this. Temperature of the solution, I believe, was 15 degrees from what I saw. Yep, 15 degrees Celsius. Let me just bring my notebook over here. Now, this is where I hope it's a little bit straightforward. The equilibrium concentration of HX, that will be found out from an ice table. The equilibrium concentration of X minus, that will also be from the ice table. And this is the first thing we can directly measure and solve for. Remember that the definition of pH is equal to the negative log of the H plus concentration of your hydrogen ion concentration. And also remember that hydrogen ion H plus is the same thing as H3O plus. We just don't want to be writing H3O plus constantly. So you should know it's the same thing. H plus is the same as H3O plus, which means we can use our pH to solve for this log of H plus, or rather for the H plus concentration. So to do this, and make sure you show your calculations, please, you take 10 to the negative pH. That's how you solve for this. So 10 to the negative 2.45 will give me my H plus concentration. So let me grab my calculator here and plug it in. 10 to the negative 2.45. That will give me 3.548 times 10 to the negative 3. So let me write that down here. 3.548 times 10 to the negative 3. Also, these are example numbers, so what I'm working with is just an example. Use your numbers. It's the same calculation, okay? So here's the thing about this calculation. That right here, this number here is my hydrogen ion concentration. Remember, we need the ice table in order to answer these questions here. Now, in order to do that, we have to remember how this works, okay? First of all, Ka is equal to product over reactant. And that is going to equal to the concentration of H plus times the concentration of A minus, or in this case, X minus, divided by the concentration of HA. And if you remember, the acid HA, HX, whatever, will dissociate in water as H plus and A minus. Initial concentration, change in concentration, equilibrium concentration. Initially, we had 1.00 molar, and then 0 and 0, we had a change. Remember, the reactant always decreases in concentration and the product always increases, and everything is 1 to 1, so they increase by the same factor. So now we have 1.00 minus x, and then we have plus x, and then we have plus x. And we just solved for x. Our pH tells us our H plus concentration at equilibrium. So if we take 10 to the negative pH, we get our H plus concentration at equilibrium. And look, right here in the ice table, you will see that this X, the H plus X, is also equal to the A minus X. So whatever this answer is here is also the same answer for X minus or A minus. So this is also going to be 3.548 times 10 to the negative 3. They are exactly the same because the ice table, okay? And that means that to calculate the concentration of HX, we're just going to do what's in the ice table right over here. 1 minus X. We already know what X is, so just plug in the formula, solve for 1 minus X. So I'm going to do that over here. 1 minus 3.548 times 10 to the minus 3 is going to give me, let me plug it into the calculator, 1 minus 3.548 times 10 to the minus 3 gives me 0.9964. So I'm just going to keep 996. 0.996 molar. Okay? And so to calculate Ka, all you have to do is plug in these values that I just solved for in this table into the Ka formula. So that is going to give me, and I'm going to use just red to plug everything in. Okay? This is going to be, remember, x times x, so that's going to be x squared. So x squared is simply going to be 3.548 times 10 to the minus 3, and this is going to all be squared. And that is going to be divided by my HA concentration, which we just said was 0.996. And this will give me my Ka value. So let me plug that in to the calculator real quick. Okay, and then I should get my Ka calculation. So in this case, it's 1.264 times 10 to the minus 5. So Ka is equal to 1.264 times 10 to the minus 5. That's how you get this part right here. All right. This is, I think, relatively straightforward. The only real point of confusion might be, where do I get these numbers from? Well, that's what the ice table is for. The ice table tells us the equilibrium concentrations. It also tells us how much the reactant decreased at equilibrium, all by the same number, x. We can solve for x by finding H plus at equilibrium from the pH. Hopefully that makes some sense. I'm going to pause the video now, and I'm going to go ahead and move on to the next one. Okay, so now moving on to part B. So part B, this is a dilution problem, dilution equation concentration problem. Remember, we have M1 V1 is equal to M2 V2. And we are given our M1s and V1s from the procedure. So this is what I'm saying. Make sure you check your procedure. This is your V1. This is your M1 for both examples. Your V2 is your final volume of this part right here, which was 30 mils. So this is V2 is equal to 30 mils. So then for both of these parts, in the top and in the bottom, dilute concentration of HX and X minus, you can calculate that by using M1V1, M2V2, and solving for M2 for both of these examples. So let's go ahead and do it for the HX. Or in this case, HA, HX, XY, whatever I'm doing here, you can do for HY as well. So we have 10 mils of 1 molar, so that is M1 and V1. We have 10 mils of 1 molar, and again, make sure you use your actual numbers, okay? And it could have been 1.01 or 1.00. I'm using 1.0 for simplicity. Is equal to V2, which is 30.0 mils, times M2. This is very straightforward. Just solve for M2, divide both sides by 30 mils. So 10 times 1 divided by 30 gives me 0.333. So this concentration is going to be 0.333 molar. Okay? And that makes sense because 20 plus 10 is 30. 10 is 1/3 of 30, which means the concentration should be 1/3 of 1, 0.33. I hope that makes sense. You will do the exact same thing for the second part right here. So the initial concentration of X minus comes from NaX. Okay? The concentration of NaX is equal to the concentration of X minus at the beginning. So that was also 1 molar or 1.00 molar. Okay? That's M1. V1, here we had 20 mils, so 20 milliliters is equal to M2. We don't know what that is. We're solving for it. But we do know V2. It's also 30 mils. Okay? So when we solve for M2, we get M2 equals 0.666 molar. And that makes sense because, again, 20 out of 30 is 2/3, which is 0.666 molar. So now we have our dilution concentrations of both of these. We have 0.666 molar over here. We have 0.333 molar over here. So far, so good. We should have taken the pH of this solution as well. I don't have an example number, but for the sake of simplicity, I want to say that this pH was somewhere around, I don't know, let's say it was 4.6-ish, right? It could be up, it could be down. These are example numbers. Please don't copy the numbers down. Make sure you're using your numbers, okay? So this right here, the temperature of the solution, I'm just going to keep it the same, 15 Celsius, right? Whatever it is. So now, to calculate the equilibrium concentration of H3O, once again, we take the negative log of the pH, negative log of H plus is equal to pH. That's what I meant to say. So we take 10 to the negative pH will give me my H plus concentration. So in this case, 10 to the negative 4.6 is going to give me 2.51 times 10 to the negative 5. So 2.51 times 10 to the negative 5. And this is in molar because it's brackets, okay? And remember, the concentration of H3O or H plus is the same as X minus, right? But you have to be careful here because in our ice table, we have HA gives us H plus plus A minus. Here's I, C, E. HA, well, our initial concentration was no longer 1. It was the diluted concentration, right? Let me pause real quick. Okay, so I just checked, and yes, it definitely is. I just wanted to make sure I gave you guys the proper information. So this right here is going to be the initial concentration 0.333. We have initially 0 H plus, but this time we don't have 0 A minus. Why not? Because we added some NaA or NaX. That is going to be our initial concentration of that, and that is why we are asking you guys to solve for this. So this is going to be 0.666. Once again, plus X. Whoops, minus X, I meant to say. Just ignore this plus right here. Minus X, reactant always goes down. Plus X, H plus, plus X, A minus. And so we have at equilibrium 0.333 minus X. And then we have X. And then we have 0.666 plus X. We can find X, and we set up Ka. And once again, we solve for what we are looking for. So we just solved for X right here. So now we can solve for Ka. Ka is going to equal to H product over reactant. So that's going to be 2.51 times 10 to the negative 5 times 0.666 plus 2.51 times 10 to the minus 5 divided by 0.333 minus 2.51 times 10 to the minus 5. And again, you're not probably going to get the same answer because I'm making numbers up, but the calculations are the same. So make sure that you actually plug in your numbers. Let me see what I get here with this calculation. I get 2.51 times 10 to the minus 5 times 0.666 plus 2.51 times 10 to the minus 5. And then 0.333 minus 2.51 times 10 to the minus 5. And the Ka value is now 5.02 times 10 to the negative 5. So here we go, 5.02 times 10 to the negative 5. Okay? And then to solve for these equilibrium concentrations, you just simply take these expressions right over here. Let me use another color. Take this expression, solve for it. So, in this case, it's 0.333 minus 2.51 times 10 to the negative 5. Yep. And then this one is going to be X minus or A minus is going to be 0.666 plus 2.51 times 10 to the negative 5. And that is going to give me these concentrations right there. And then, of course, just to double check, if you plug this in and you plug this in to the Ka formula, you should be able to get those answers as well. So hopefully you kind of see where this is going. We're just using ice tables to solve for X, and we're taking into account the initial conditions and final conditions and just plugging in the numbers. Okay, so I'm going to pause the video one more time so I can switch over to the next part and we can continue on solving this. Okay, so for part C, it's very similar to part B, so make sure you read carefully. We start with 10 mils of 0.33 molar HA from part B. In these same 10 mils, this is the same 10 milliliters, okay? This is not a separate amount. This is not a separate aliquot. This is the same 10 milliliters, okay? In the same 10 milliliters, there is also a concentration of 0.666 molar A minus or X minus. We are adding only 10 mils of the solution that contains both of these concentrations to 50 mils of water. Now we have 60 milliliters of total volume. So now that we do that, we can actually go ahead and do the dilution calculation once again. we have our M1s right over here for both of them, and we have our V1 for both of them. Here we have our V2 for both of them. So for this one, it's just going to be M1, it's going to be 0.333 molar times V1, which was 10 milliliters, is equal to M2, we don't know yet, V2. So V2 is going to be 60, so 60 mils times M2. And make sure you use your units, please. 60 milliliters times M2. Solving for M2, we're going to go ahead and do that. So 0.333 times 10 divided by 60 is going to give me 0.0555. So this is going to be 0.0555 molar. And same thing for this one. For this one, it is going to be, let me use a different color. This one right here is going to be M1, it's 0.666 molar. V1 is also 10 milliliters. They are in the same aliquot. And then M2, we don't know what M2 is, but V2, we know it's 60 milliliters times M2. So solving for M2, we get 0.666 times 10 divided by 60 gives me 0.111 molar. So this is 0.111 molar. Okay. pH of solution. Again, I didn't take this number. Nobody offered an example. So I'm gonna go ahead and say, I don't know, I'm thinking at this point it's very close to water. I'm gonna say the pH is 6. Temperature, let's leave it the same. Okay, so once again, we start by calculating the equilibrium concentration based on the pH meter. So 10 to the negative pH is going to equal my H plus concentration. So 10 to the negative 6, let's go ahead and do that. 10 to the negative 6 is going to be 1 times 10 to the negative 6. Again, use your own numbers, okay? So 10 to the negative 6 is going to equal 1.0 times 10 to the negative 6 molar. Okay, use your own numbers. And in this case, we didn't add any more A minus. Okay, we just have a new concentration at the beginning. So make sure you include that also in your ICE table calculations. So let's go ahead and do the ICE table before we solve the next one to make sure we do it correctly. We have HA gives us H plus and A minus, I, C, E. For HA, we have an initial concentration of 0.555. So 0.0555 minus X gives me 0.0555 minus X. For H plus, we have 0 at the beginning, and then we have plus X, and now we have X. For A minus, we start with 0.111, and then we have plus X, so the final expression is 0.111 plus X. To calculate the equilibrium concentrations, we have to solve for X first. We already solved for X. So the concentration of A minus is going to be 0.111 plus X. X in this case is 1.0 times 10 to the minus 6 molar. So let's go ahead and put that calculation in place. Plus 1.0 times 10 to the minus 6. It's just 111001. So basically the same. It's a very small number, right? So this would be 0.111001. Okay. And then sig figs, it would just basically stay the same, but I'm using the whole numbers just to emphasize that it's changing by a certain amount. This one, same thing, 0.0555 minus 1.0 times 10 to the minus 6 is going to give me, let me go ahead and plug that in, 0.0555 minus 1.0 times 10 to the minus 6 gives me 0.55499 molar. So now I have my equilibrium concentrations. So now I can solve for Ka. So Ka is simply products over reactants. So my product is going to be 1.0 times 10 to the minus 6 times 0.111001 divided by my HX concentration, 0.55499, and that should give me my Ka value. So let's go ahead and plug it in. That is 1.0 times 10 to the minus 6 times 0.111001 divided by 0.55499 gives me 2.0 times 10 to the minus 7. Okay, there you go. That number seems off because I'm making numbers up. I don't actually know what the pH of the solution was. I said 6 because I am adding way more water and water should be around 7, but it's possible it could be a 5. So this number should not be times 10 to the minus 7. It should hover around times 10 to the minus 5 times 10 to the minus 6. So make sure that you're checking yourself based off of that. But this is how you do part C. I will now once again pause the video so I can continue on to part D, and I will complete the calculations of this video.